I first learned about the VUV technique through Bill Winifred. So he was a former research fellow at Dow Chemical. He and I had worked together down at the Dow R&D Center in Lake Jackson, Texas. And Bill was using this technique to solve some very complex problems. So I'm very interested in seeing some of the stuff that Sean's going to introduce today. So the title of this presentation is going to be Understanding ASTM D8519, Determination of Hydrocarbon Types in Waste Plastic Process Oil using gas chromatography with vacuum ultraviolet absorption spectroscopy detection. So the virtual floor is all yours, Sean.
Well, thank you very much again, everyone. And I'll get through this pretty quickly, so hopefully everyone can hang on till the end. And you should be able to see my slides in presentation mode about now. Yes?
Yes.
Very good.
Very nice.
Very good.
Yep.
So again, given the nice introduction, again, I thought I would start with throwing myself on the grenade for this clip, and it's got audio. I hope we can hear it, but let's see. Yeah.
Good old mass spectrometry. We've got nothing against it. We just think it's time for a worthy alternative. Get ready to share.
So again, I apologize, but I had to show that because I get reprimanded every day for ever making that video because again, we were totally new to this industry. I had no understanding of how deeply entrenched and sophisticated mass spec is in the world, but I've since learned. So just a little bit about VUV Analytics. I'm one of the founders. We started the company in 2009. We were formerly in the semiconductor space where we learned how to work with VUV light, vacuum ultraviolet light, and sold a company there in 2009 and started this company. We bootstrapped it for a while and placed some betas and filed IP and finally released a product in 2014. And then, continued to file patents. We've got now 43 patents actually granted, and 3 more now are pending for a liquid chromatography technology as well. We're well entrenched in the market. We've shipped hundreds of instruments now, but we are headquartered in Texas, in Austin actually, because of the semiconductor hub. But because we're in Texas, we had to land in the oil and gas world pretty significantly, and that is a bulk of our business. We have about 120 peer-reviewed journal articles now related to the VUV technology, and actually 5 ASTM methods now and 1 EN method, and we continue to focus on those entities to establish methods. They make it easy to sell instruments when you've got methods associated with them. So the core technology we're talking about, I always start talking with the reminder that this is just absorption. This is just Beer's Law, very simple stuff. But I always like to make fun of this. There's a textbook that every chemist in the United States has studied, and that's Principles of Instrumental Analysis by Doug Skug. He was the chair of chemistry out at in Stanford. And in every version of that book, he references something like this. Energies associated with single bonds are restricted to the VUV region, but experimentally it's so difficult we're not going to talk about it anymore. And that's kind of been the history of vacuum ultraviolet light, is that experimentally it's difficult. But what we're talking about here, if you get into low enough wavelengths, i.e. high enough energies, everything has a chromophore. We were able to excite everything. These are electronic transitions. And we're talking about sigma, sigma star, pi, pi star electronic transitions. So these are very strong absorption responses and very, very stable absorption responses. And I'm going to talk to that in a minute. It's very important of how stable these responses are. And they're the same. They're the same for every instrument in the world. And the absorption shape we see is strictly a function of that molecule excited by these energies, not the flux or any of that. It's strictly those wavelengths exciting that molecule that give rise to the shape. And this is not a function of the matrix, so that's not impacted by the matrix at all. And this is where we differ from mass spec, right? There's no ionization efficiencies that we need to worry about with regards to matrices. We just see a linear addition of one response plus another response. There's no change in either of those responses. So fundamentally, that's a very important principle to how our instrument works. we have a very simple detector that fits on any really GC in the market, can fit on either the left or right side, and two different platforms. Really, the differentiation here is the temperature. We have VGA 100 that's kind of suited for the sub C30 hydrocarbon range. And then one that has a transfer line and flow cell that goes higher to 430C, where we do some of the heavier product. And the pi oil method is built on this VGA 100. They're, again, fundamentally the same, except for primarily this temperature control difference. But if you compare our instrument, this little box that at one time was on a kitchen table being developed, to synchrotron data, what you'll find is the data is exactly the same, right? And this is a multi-billion-dollar light source. You can see the agreement in our data, for example, in acetone here. The only spectral differences that you're going to see here are resolution related, right? The synchrotron can be incredibly high resolution instrument, while ours in general is about 1/4 to 1/2 nanometer resolution. So the instrument, again, is really pretty simple. People get mad at me when I call it a light bulb in a box, but it really, from a robustness standpoint, that's exactly what it is. Oh, I'm sorry, I'm jumped ahead there. That's exactly what it is. If we start at the top again, we're just talking about absorption, so nothing novel there. But if you look in the electromagnetic spectrum in the ultraviolet region, there's kind of a UVA, a UVB, a UVC that everyone's familiar with. Well, below that is a region that's actually called the vacuum ultraviolet region, and that's the region in which we work. But we do that without vacuum pumps, which is also a very interesting comment. It's really related to most of our IP, is how do we obtain and measure and control these signals without the use of vacuum pumps. And it has everything to do with outgassing control and contamination control and all of that. So, but really, again, it's just an ambient environment instrument. We have a deactivated column inside a heated transfer line here. So that deactivated column would just tie directly into your analytical column. Things will flow out of that through our flow cell and out. Our flow cell is only 10 centimeters long, 40 microliter volume, and then we have a deuterium source. But the difference of this deuterium source is right at the nose, we have removed the quartz envelope and we have them fuse on mag fluoride. So it has a mag fluoride cone on the end. A lot of people are using similar sources for photoionization sources. So it's not uncommon, I think, to this world. But we do have to use reflective optics. You can't use transmissive optics in this space. So we shine that light down to a parabolic mirror. We send a collimated beam of light through the flow cell. There are mag fluoride windows on either end of our flow cell again. And then we bounce that light up to a very high resolution fixed position grating that there's no movement in this instrument. And that breaks the light up by equal wavelengths down to a CCD array detector. Again, so we're taking more than 2,000 pixels of data on this CCD from 125 to 240. So that's the 1/2 nanometer, 1/4 nanometer resolution, which I spoke about. And you can control the acquisition speed of that CCD array. Most methods are running at 5 to 10 hertz, but we do have several instruments on GC by GC hardware, and you can run this up close to 100 hertz acquisition rate. The beauty is that, again, in this energy space, everything absorbs, even the single bonds, so even the saturates. But Mother Nature did us a little bit of a favor, and that is that the carrier gases are the only things that are really invisible: helium, hydrogen, nitrogen, argon. So when we are looking at absorption, there is no mobile phase effect here, right? We are just looking at the compounds of interest. And we do have very qualitative, quantitative data. I'll show you spectra in a second, and we'll talk a lot about that. And then again, it's just Beer's law. It's very linear, very predictable quantitative technique. And as you can see, there's really no moving parts. It's a very robust technique. There is only one moving part, actually. It's not shown here. And it's just a shutter that we have, a pneumatic actuated shutter. So at the beginning of a run, we take a dark noise reading, then we open that up and start taking measurements. So again, very, very robust instrument and no vacuum pumps again. So, most people always ask, well, what do my compounds look like? So, most people have not, if you've not worked in synchrotron studies, you've never seen absorption down in this range. And this is just an example of a couple of applications. And in some cases, these are going to be incredibly rich looking spectra. In other cases, less rich looking spectra. But very important to note that this delimiting, for example, those small little changes that you see in there, these little inflection points along the way, those are stable. Those are very real, and they're a function of the electron orientation again. And we will be able to discriminate isomers, including stereoisomers. The only thing that looks different to are the same to us, I'm sorry, are true chiral compounds. So no matter how a chiral compound flows through our flow cell, it would appear the same. But other stereoisomers, in fact, do look different. And even to your eyeball, many times you would not be able to see the difference, but spectrally there is difference, and we've got a lot of the published journal articles out there that push that to the limit. Particularly the people that are doing work with fentanyls right now, the various fentanyl analogs. There's a lot of very similar structural information in those. Some of them look visually to the eyeball, they look the same, but these researchers have shown repeatedly that we're able to identify those properly from each other. And like I mentioned, a lot of work in the isomer, a lot of the publications are using the benefit of the VUV for isomer discrimination. Again, for example, these cis and trans fatty acids here, they're similar to your eyeball. To our instrument, those are worlds apart. We would never, ever confuse these two molecules. And in fact, if they were co-eluting, we could even do a deconvolution of those, just a linear regression deconvolution of those, because they are so different from each other. And that is a basis of our instrument. Now, we've had a lot of success in the hydrocarbon space, and this is kind of the reason why. Yes, isomers look different, but classes look similar. And that is really a big key here. I apologize, I've got a couple of auto loops, but classes look similar. So you can see on the left-hand side, again, these single bonds, the saturated molecules, your linear, branched, and cyclic. There is, I apologize for the screen rotation. Sorry, the saturated molecules. If you look at the linears, there's a very steep slope associated with them. The branched, I'm going to pause this while we talk to it. The branched have, again, a little bit less of a slope. The cyclic, even less of a slope. So for, golly. I'm sorry, I don't know why they're rotating on me, but and then when we start to talk about and so through the gasoline range, we can discriminate those. Through the above C15, we will group these two, right? The branched and cyclic will start to look similar, and they also become physically kind of similar, as you might have a single a cyclic bond, a cyclic saturate that has all kinds of branching around it. Functionally, it starts to become very much like a branched saturate, and those do become similar. We can report the linears out all the way through. This and the aromatics is caused by the double bond, that absorption response you see there. When there are a pair of those that are conjugated, you will see a red shift. I'm just going to, instead of exiting and fixing this, I'll just keep clicking, sorry. But when you do see conjugated double bonds, you'll see a red shift there. Similar with the olefins, you have your double bond, and then you have the aliphatic response kind of region contributing here. And when we have diolefins, if they're not conjugated, that peak doesn't change. The low wavelength information does. If they are conjugated, you do get a response shift to the red shift. So we've got a very good footprint in the hydrocarbon space now. You can see kind of the customer list here. We're in all the top U.S. refineries, most of the top global chemical companies. The test labs have them. And again, we have 5 ASTM methods and an EN method. The ASTM methods are the Piona analysis 8071. Then we have a Piona analysis for European fuels with all the various oxygenates in there, the ethers and alcohols. We do a DHA analysis. detailed hydrocarbon, where we're speciating everything in the gasoline range. We do jet fuel certification, diesel and biodiesel, and then our waste plastic pyrolysis oil method. So in the hydrocarbon space, again, this is really why people are embracing this so much. We do, again, have methods that cover kind of the whole solution range for them. These methods are calibration free. And the reason they are calibration free is go back to the stability of that absorption response. Once we have characterized the absorption response and the relative response factors, they are the same for every instrument in the world. So we build a library around those absorption responses. And if we're doing a mass balance calculation, well, then we have no calibrations required whatsoever. We know exactly what the molecules look like. We know their relative response factors. We report that in a mass balance, i.e. no calibrations. And that is a beauty for the fuels labs, of course. There's no sample prep. We're just injecting these things neat on a splitless injection. For these pie oils, if you're going heavier than C44, we would recommend a PTV type inlet. But for most of the customers in the world, they're dealing with sub C40 material or C40 range material and just doing splitless. The data processing is fully automatic. I'll talk about that and show you that in a second. There's a beauty in that there are no user dependencies. I'll come back to that. We are a mass sensitive detector, so everyone who typically is familiar with absorption, of course, thinks concentration. But if you kind of go through the mathematics, when you don't have a response from your mobile phase, from your carrier gases, mathematically it kind of turns into a mass sensitive detector. But in that those libraries that we build, we also have density values. So we can easily toggle back and forth between a mass or volume reporting with no effort, no setup differences or run differences. All of our methods are just using a single nonpolar column, which sounds crazy to people that have been doing fuels analysis in the past. We're not using any traps or valves we're just using a simple nonpolar column, getting boiling point separations, and then solving for those complex chromatograms spectrally. And this data is persistent. This is very important and sometimes overlooked. And it goes back to this no user dependency. You need to understand when we run a sample on a chromatogram, we're doing data acquisition, this high resolution acquisition. That data becomes like an electronic retain. You could, for example, let's say, I'll give you a quick customer case. If you set up a DHA on a product and you have typically, let's say, 0.5% of unknowns, then you come back a year later and you're running that. Now you've got a 3% unknown or something associated with that. You could actually email us that file and we could go scour that and see what's crept its way into your process. And let's say we found styrene or DCPD or something that's not in the fuels library. We could add that to the library. You could then go back and reprocess all of your past results to find out where styrene or DCP started to creep into your process. And then you can really do kind of a source analysis of some of the contaminations. So it is a very different set of data. I believe we're really the only technology that kind of enables that capability. And then there are some cost advantages, and largely because we're not using any solvents and there's really no big labor effort to run our instrument, that there really are some cost per sample advantages. So how does this magic work a little bit? And again, let's start with Beer's Law. We're talking Beer's Law. It breaks down in kind of a set of unknowns. Well, when we first set an instrument up, we will go run a couple of standards on it. We will run a retention time standard. It's just a linear alkane standard, and we'll store that file. I'll refer to that in a second. And then we run a very simple gravimetric mix. And in this case, we use it to look for discrimination and other things. But there's one very important thing. We have in this VUV1, for example, a known amount of benzene. And we're expecting to see just the benzene peak area at some value. Now, our instrument has a makeup gas setting, a dynamic makeup gas setting. And again, we're talking about invisible makeup gas or invisible carrier gases. So if the benzene response is higher than our target, we can increase the makeup gas, dilute that response down a little bit, or vice inversely, if it's too small, we can decrease the makeup gas and drive that response up a little bit. But once we've done that, really what we've established is make certain that everybody's instruments are operating generally under the same conditions. We're kind of describing the flow rate now. And that becomes important because if you look at Beer's law, we know the cross section of the molecules. That's the library that we have rigorously built. We know the flow cell geometry, we designed that, and now we know the total flow rate through the instrument. So the only unknown becomes the mass of the analyte in the flow cell. So it reduces the whole thing to just a very simple first principle determination of mass of analyte in the flow cell, and that's linear. So the mathematics behind this is actually very simple and powerful. We can take a complex chromatogram like this gasoline that's run in 30 minutes here. There are hundreds of coelutions, maybe thousands of coelutions that are occurring here, but we don't really care. We are looking here at the top of just a 2 to 4 minute approximate timeline of that chromatogram. And you can see in the blue line, there are all kinds of coelutions occurring in this. Our instrument doesn't care about that. What we do, using that retention file that I referenced, we will look at this time slice. This green, thin green line that you see here, that is what our CCD measured at that time slice. So what we do is we go into our library at about a plus or minus a half a linear alkane. So we're basically saying what possibly in our library around this time could look like this shape. Well, let's go fit that. If we can find one compound with that shape, then linearly, how much is there? Well, then we check a goodness of fit. And is that an adequate fit for that? And if it's not, then we go back and look at any possible pair of molecules in that retention window and at all possible linear combinations and say, are there any two molecules that at some linear combination can fit that? If the goodness of fit is still not good, then are there any three combination of molecules that could fit that? And just as an example, if we look at this thin green line, if we tried to fit that with a single component, we're at 0.7 something goodness of fit. With two component, we're at 0.92 goodness of fit. But at three components, we can get triple nines. Okay, pencil down. We've solved that time slice, move to the next time slice. We have no kind of a priori knowledge of this. We're not having any carry-on knowledge or feed forward, feed backward. So if you've got, long tails or anything, we're going to solve for that. We're not making any assumptions about Gaussian shapes or any of that and not working off of any fixed peak table. We're simply solving for spectral matches. And just to give you an eyeball of what that looks like, this purple line is exactly what our CCD saw at that time slice. So this is what we measured at about 2.6 minutes. But now if I show you the library components of the solution, the green is pentane, the blue is the trans-2-pentene, the red is the 2-methyl-1,3-butadiene. And now you can kind of visually see if I add these three components together, I'm going to get that purple shape. And that's exactly what we do, time slice by time slice at the end of the run. It takes about a minute or so to run, but we will report at the end of this your Peona table by mass or volume. You can toggle those. We would show you anything that you've called out to be speciated. Again, I apologize. Anything we would call to be speciated in there. And you can also, if there is concern over any of these, you could simply go to, for example, if you thought the olefins were artificially high or one of those may be wrong, you could double click, for example, on the C6 olefins. It'll pull up a window of all the C6 olefins it found. You could click on any one of those. It'll take you directly to the time slice and let you look at the spectral fit for that component. So true verification of the data, and we refer to verifiable data a lot. You'll see the green line, the blue area is our calculated solution. The red line is the residual, point by pixel delta. So it allows you to confirm that, yes, that compound is in fact there. So we have an instrument, again, that on a 30-meter column can run gasoline, jet, or diesel or biodiesel for your standard fuels applications. And then if we run a 60-meter column, we can do a full DHA on the gasoline range material where we're speciating, again, everything. And we've heard great feedback from Valero and others that they're really able for the first time to get, close the mass balance around their process units because they're getting really accurate data, spectrally verified DHA data. Now, the pie oil. So I'm going to borrow, if everyone doesn't mind, some Loomis slide here, but Loomis has got this nice summary of what we're talking about largely with our method, mixed waste plastics. Again, there's multiple routes that you can take this. Again, all of you are certainly familiar with this. There's the carrot or the stick of why this thing is going to keep growing over the next many, many years. And if you look at the predicted CAGRs, it's a pretty healthy market that we see ahead of us. And a lot of the majors have pledged to have a certain amount of this either co-processed or what have you into their business units. A lot of players on this front. This list is changing every day. The group on the left are largely focused on taking these back into the fuels and naphtha products. The group on the right are more focused on taking them back to the monomer level. There's a lot of overlap between these. And again, these lists change almost every day as some of these are getting acquired or going under or what have you, but very active. Again, from valorization, you can take these products back into a refinery or into your cracker. The big challenge in the world is this, that there's not a good sorting technique on these mixed waste plastics. You're going to have contaminations at various levels of, mixed polyolefins as well as styrene, PET, biomass contamination, you name it. So we do need to figure out how to handle that. Now, you also, I'm sure all know that, with variations in whether it's a polyethylene or polypropylene, you're going to get variations in your piona. If they're PET, you're going to get variations in your piona and get some oxygenates. If it's low or high density, you're going to get variation. I mean, it's just, these are highly variable products. Now, the factories know how to run these things. I mean, they know the contamination control strategies. They know how to do molecular cut points. They know how to, what they need is better data on the incoming pie oils so they can figure out how to process these things. Well, Dow Chemical has published a couple of papers regarding VUV. They've basically come back and said that they're kind of wholeheartedly moving to VUV for feedstock analysis for a lot of these reasons. We, again, are not working off of a fixed peak table. We do deconvolution. So, for example, like in heavy naphthas, where you've got a sea of saturated isomers as a background, we will do a proper deconvolution of those and accurately measure your aromatics or olefins. In this data that Dow has again published, if you look at the classic liquid hydrocarbons, very predictable distribution of these. Whoa, now you get to the pie oils, and of course you have the high olefin content, but what's more important is if you look at within class, the variation that they see. I mean, it's a 30% difference across the individual classes. So again, just a lot of variation on the incoming product that needs to be understood. So the world has thrown a whole suite of analytical techniques at this, trying to figure this world out. This is where this interest group comes in, I'm sure. But yes, SIMDIS is still run on these. DHA is attempted, even though it was woefully inadequate. GCMS, 2D-GC, NMR, everybody's looking at everything to fully characterize these. And this is where our method comes in. So this is our method description and scope. It's D8519. Again, it's using the exact same GC-VUV description that I've walked you through. And basically, we have a main body that looks at a product basically going up to 545C. So kind of C44 range is where we really kind of trip the difference here. And then an appendix that goes all the way up to C64. The difference being, again, splitless inlet, PTV inlet, right? That's why we have a main body and appendix. But here are the classes that we're going to break out. We have decided, of course, you get your aromatic breakouts, your saturates. We also not only report total olefins, but we're reporting conjugated diolefins. Those are of particular interest, although they don't survive particularly well, but people are interested in them. And then we've separately grouped out styrenes just because they're always present. And frankly, some people love to see them in an aromatics bucket. Some people would kind of call those olefinic. So we just call them styrenes, and we group that bucket out. Now, this method is pretty robust. We're using, again, the same library. We're not making any assumptions or peak tables. So we have 3 very different looking pi oil chromatograms here, and we're able to step through that regression approach that I talk about, solve these time slice by time slice, and end up with these Peona tables, if you will. And you can see these are very different. In some cases, the monoaromatics is 5%, 96%. So these are, very, very different looking products depending upon whether they've been hydrotreated or not, and what the sources are, etc. Now, one other unique thing about our data is we're not just reporting group totals. Because we are going time slice by time slice with a nonpolar column, I can actually show you your aromaticity profile or your olefinic profile. I can show you by boiling point where those things are actually occurring. So, decisions with regards to molecular cut points, I can provide very interesting data by class of the boiling point distribution. And it also, for hydrotreating purposes, lets you get a good eye on where your process is having success or not knocking down these double bonds. And then, of course, your polyethylenes, there's the common triplet that everyone sees. There you've got your linear alkane, your linear alpha olefin, alpha omega diolefin. Again, we're easily solving for those as we step through them. Just one other data point. Once this data has been collected and run, every acquisition or every time slice has a red dot, green dot, blue dot. Blue dot is where we do a background. Green dot is where we satisfactorily solve for the goodness of fit. Red dot is, for one reason or another, we didn't solve according to our goodness of fit. Usually that's a signal to noise. It's right at the baseline. You'll see red dots, but periodically you might see red dots over a peak, and that means something's missing from our library. And yes, users can modify and add to our library all they want. They just can't save it under the same name for traceability purposes. But in this case, I'll just highlight these 2 below. Chromatographically, these look identical. They both have this kind of signature polypropylene fingerprint of the 2,4-dimethyl-1-heptene, and they have about the same area reject that's coming from the tail, low signal to noise. But in this one and below, we see benzoic acid. So we know that while their hydrocarbon distributions are very similar, almost identical, this one probably has more PET contamination, right? So we are not a trace level analysis. We are not a heteroatom selective detector, but we are able to include into our library those things which come at detectable levels, report those as kind of a canary in a coal mine that you may want to take this sample for further oxygenate screening, as an example. And that's exactly, and again, this verifiable data, you can click on that benzoic acid. It takes you directly to that time slice. You can see the green and blue fit here. You've confirmed that is absolutely benzoic acid. I have high confidence in that. Therefore, we probably want to, again, take that for additional screening. And that's what this comment, this slide is about. We know these things, depending upon their source, have varying levels of different heteroatom activity. Again, we are not the ultimate solution for heteroatom activity, but if detectable at kind of a 0.0x% level, 0.01, 0.02, we will report those. So we've added several things into our library. Again, to whether, phenols and cresols to see whether you got biomass contamination, the terephthalates, the benzoic acid to see if you've got PET contamination. The styrenes, again, have been individually added to report and sum those up for the styrene. So we do kind of provide some level of process indicator of samples more or less contaminated, if you will, by heteroatoms. And then just in ASTM, this was just a quick comparison. One column is a source provider of pi oils. The other column is an acquirer of pi oils. You know, in some cases they're talking the same language, in some cases they're not. So ASTM has taken it on to say, okay, let's come up with a proposed guideline for the characterization of these. Not all inclusive, but at least let's get people starting to talk the same language. And we've been blessed that they've, you know, kind of nominated 8519 as the hydrocarbon analysis technique for these pi oils. So it may allow 8519 to start to go on to some COAs, for example. And yes, there's been some method validation, largely through and with AmSpec. We work quite closely with them in Houston. They've got now 4 of these instruments. They went through and showed linearity through the C44 to make certain that the split-splitless works. They made certain that our endpoint lines up with their SIMDIS, right, to make certain that, you know, just again, validating this. They went through a verification to show that our data agrees with D1319, the FIA approach, which still, as an outsider to this business, just blows my mind that that technique still works. But by God, it does. It still works every time you run it. I mean, it's really remarkably robust technique, and we agree very, very well, of course, with that. And then they did some repeatability studies. So, and you would expect this kind of excellent repeatability because there's no user dependencies, right? We're just spectrally fitting. So they ran samples over a month's time, even 2 different injection volumes, and you can see the kind of repeatability that we've gotten on these. So incredibly repeatable data. And then the last data point here, I think, is kind of interesting. I've never seen this test, but they basically have a PIO product, and they went through and ran it with our method to come up with these group totals. And then they did a fractional distillation, and then they ran the front end of that and then the back end of that on our methods. And when they go back and recombine these two at this ratio, they get almost exactly the same data. So it just basically showing that even if you're chopping your product up into narrow fractions, our method is still totally applicable. We don't have to do anything different with our method. Again, it's working off of this kind of no a priori knowledge use of this library. So I did it. I got through all very, very quickly with 1 minute over time. So I give, you know, maybe just answer it up open it up for questions here if anyone's got questions. But, and I know it's very, very quick. I apologize for the frenetic pace, but hopefully you got the point on all of it.
Yeah, that was an outstanding presentation, Sean. Thank you so much. Yeah, anybody have any good questions? I know Joe practices this technique quite a bit, so he may have some.
He's going to hold me in check. If I lie,
yeah, you're going to say he'll ask you the good
one.
Sean, just out of curiosity, since we're dealing with Beer's law, is there some dynamic range? Because obviously we know there's a carryover when you get above a certain level of concentration. So is it just because if you do since you adjust that, I guess, carrier gas, is that how you keep it within that range?
No, we get about 3 or 4 orders of dynamic range. So first off, yeah, we get about 3 or 4 orders of dynamic range, but it's kind of hard to show. We are looking at a pixel by pixel level for saturation. And so what we're able to do is, even if, for example, and I'm going to hand draw a spectra real quick, but if we look at benzene, the monoaromatics, remember there's that strong peak that the top of that's going to start to saturate, right? Become opaque in those wavelengths. And so we know those pixels are saturating, so we exclude them from the fit. And so there's still enough fine structure information for us to go solve the remainder of the spectra and get that right. Now, what's interesting is in some of these pi oils we found in our interlaboratory study, customers will come and periodically they've done a hydrotreated product or something, and you may have a big benzene or a toluene peak that goes into saturation. If we've automatically put into our software, if there is a flag, basically at the report level, when you get the results, we will automatically tell you of whether we have a high confidence in that data or not. If we think there was too much saturation, and there's a couple of knobs we have there, one of those is X number of pixels saturated at any time slice, or time slices in a row which have saturation. If there's any reason for us to believe that that data is at risk, we'll tell the customer to go re-inject under a different split ratio, right? So we do monitor and look for those saturation occurrences where they could be causing us problems.
Okay. So I guess I noticed that some of your time slice data. I'm sorry, Chris.
I'm sorry?
No, that's what I was going to say. You have to split them at a lower concentration to have the data.
Correct.
Yeah, that's, I guess I noticed when you were showing some of your data, the time slice was off the peak maxima, right? It looked like it was a little bit off to one side or the other of your chromatographic peaks. And I'm guessing that's intentional based on what you just described.
Yeah. Again, if I walked through a chromatogram with you at some point, you would see that we're solving everything properly, but in some cases we start to exclude several pixels in that fit. But there's enough fine structure in those that we get them accurate every time to a point. And then at some point, if there are too many pixels saturating, we throw up a flag and say, please rerun under a different split.
Great.
Okay, great. Thanks.
Very
Thanks,
nice.
Sean. Appreciate it.
Thank you.
Thanks.
Very simple, yeah, very nice. Very competitive with mass spec.
No,
pretty good.
Yeah, no calibration needed, but we are sold to mass spec. I have to go.
No,
Yeah.
I'm never
gonna
very
say
much,
that.
very
Bye, Chris.
much.
See you, Chris.
Yeah.
Thank you.
Interesting.
Yeah, it's complimentary for sure.
Yeah, definitely. Yeah, because I know we do a lot of GC-MS with looking at pyrolysis oils. Maybe that's another topic for another meeting, Tony. We can always discuss.
Oh, absolutely. That's another technique. I would peek over people's shoulder, all the stuff with GC. And I was telling Sean, that's how I learned about the VUV, because Bill Winifred would have it. It'd be in the mass spec lab, but it was over in the corner. He's like, I got to check out what these guys are doing. You can solve some amazing problems.
One comment on that, though. We're working with Topso, in fact, right now. As you start to get some of these bio-based pyrolysis oils, then you start, as you know, you get a bunch of these non-polars in there. And so in theory, you really would like to have a different phase, right? Instead of this non-polar column. And so they are basically, and one of the problems with pyols, again, if you're doing a standard 2 GC by GC setup, you're not going to get separation of your olefins and your naphthalene. You're still going to have coelution occurring there. Yeah. And what we can do is lay the VUV on top of the GC by GC. So we would spectrally separate those regions automatically. And if you think about it, we basically are where you're looking at GC by GC today, you get these images, these heat maps kind of, and you draw your templates. We could eliminate all of that and report to you just a matrix of results, of fitted results. So you no longer have to look at maps and heat maps, and you no longer have to draw templates. We can just report back to you our spectral deconvolution and solving and quantitation on top of your GC-GC separation. So for the mixed biomass-based py oils that are coming in, that's a really good solution, because then you can get your polar, non-polar, things have nice peak shapes, and we can expand the library to include all of these other phenols and cresols and all of the other things that would start to pop up there.
Yeah.
But still automate the analysis. Yeah, still automate that analysis. Yeah.
Yeah, I obviously haven't run any of the GC data myself, but my colleagues in our application lab and elsewhere have run stuff. And so I'll maybe, Tony, what we can do is when this recording is available, I'll share it with like Chip and a couple others, and we'll take a look at it. So, because I'm sure they'll be interested to see this. And then, like I said, from a complementary standpoint, show some maybe pyrolysis GC-MS data, if that's something that we want to do as a future topic for the group.
Oh, absolutely. Yeah, because the recycling's not going away.
Yeah.
No.
It just keeps getting bigger and bigger. That's why I saw, that's why I contacted Bill Winifred and Sean. I was like, this is it's just growing and growing. That people need to know more about these techniques. They're really powerful techniques.
And listening to IRPC talks this last week, I mean, it's kind of all the catalyst guys. This is their whole focus, it seems.
Oh, absolutely.
Right now.
Yep.
Well, very good. Well, awesome. I'm satisfied. Thank you so much, Sean. That was great. I appreciate it.
Absolutely. Absolutely. Thank you guys for helping set this up and listening. And sorry about the slide rotations, but instead of stopping and turning it off, I just.
Yeah, you'll have to like go
back
into your PowerPoint, and then there's like a slide, there's an area for like stopping like automatic slide transitions. It's under, I forget which tab it's under. I'd have to look at PowerPoint myself. But yeah, that's happened. That's happened to everyone sometimes, you know, especially if you're borrowing slides from people and putting it in. Sometimes they have those animations already built in, and you're like, oh, when it happens.
Wasn't expecting that. Yeah.
Yeah. No worries.
No, I appreciate your patience on that. But yeah, no, I'd be in it, and we've got a pile of data on all these comparisons. So if you do want to come back to this, you'd love to stay involved with the team here and share with you any of our comparison data.
Perfect. Yeah, no worries. And then Tony, I don't know if you can stop the recording, or hopefully when the meeting ends, it will. And then Celine or whoever is in charge of this meeting, organizer wise, they can get that video out, I guess, to everyone. Yeah.
Oh, absolutely. Yeah, because there are a lot of people that are going to be interested. Unfortunately, usually it's a pretty good group. I'm assuming there's just the timing, but I promise you, they will watch these videos, and they may contact you afterwards, Sean.
Yeah. There was no for whatever reason, there was no email. It was just through that LinkedIn post. So some people might have missed it. So just to let you know.
Okay, that could have been it. Okay. We'll do better next time.
Yeah, because I saw it on LinkedIn, and then so I just created my own like calendar appointment, so to remind me that this was happening.
Okay.
Well, I'm always happy to sing and dance outside of this recording. So if anyone has any additional questions or wants to go deeper on anything, I'd be happy to coordinate some time.
No, of course. Yeah. Well, I mean, we'll probably see you at PitCon, or probably the next conference, I would imagine, unless you're at Gulf Coast Conference. And
I will be.
Gulf Coast.
Yeah, we'll see.
We'll
see you there.
Down there. Yeah.
I'll see you
very
there.
Good. Very good. Yeah. I will be there. Absolutely.
Perfect. All right. Sounds great. Well, thanks, Tony. Sean.
Oh, no problem.
Yep, Brian, nice to meet you. Tony, again, thank you very much for helping coordinate this.
You have a good day.
Yep. You bet. Cheers. See you in Galveston.
See ya.